Hey everybody, Mr. Longo here to talk to you about what exponential function type of graphs look like. So your parent function is y is equal to a times b raised to the x power. Now there's a couple of rules. A is not allowed to be 0 because then you wouldn't even have a function. B has to be a positive number. It must be greater than 0, but it also is not allowed to equal 1 for a very important reason. If b is greater than 1, you have exponential growth. If b is less than 1, but still positive, so we're talking fractions, 1/2, 2/3, 3/4, that's exponential decay. So if it's between 0 and 1, that's exponential decay. If you have 1, then you're just multiplying everything by 1 and you're back to a linear function. Okay? So what are these graphs going to look like? Well, naturally, exponential growth is going to continue to increase by multiplying. So it's going to get bigger and bigger and bigger really, really fast. But this is kind of hard to imagine sometimes, but it's never going to be 0 either. So if you were to raise, say, 2 to the -1, that's 1/2. And then you were to take half of that, you're at 1/4. Half of that's 1/8. You will never get to 0. You'll get really, really close, but you will never be at 0. So you're going to have a horizontal asymptote at y equals 0, which means your range is going to be y has to be greater than 0. Sometimes it's less than 0 if we reflect over the x-axis. Your domain, of course, is going to be all real numbers because you can raise any number to a positive, 0, or negative. On the graph, unless we have some sort of transformation, 0 is always going to go through 1. And the reason that's going to be is because anything raised to 0 is 1. 10 raised to 0 is 1. 1,000 raised to 0 is 1. And then 1 is going to give you your b value. And then after that, you just have to look at the graph in the calculator. Now, here, for all of the graphs that you do, I recommend just typing it in the calculator. That's why I've got mine ready to go. Exponential decay, very, very similar, except for it's going to decrease as we go. So if you think about it, if it was 1/2 to the x power, 1/2 to 0 is 1. 1/2 to the first power is 1/2. 1/2 squared is 1/4. 1/2 cubed is 1/8, and it's just going to keep on getting smaller and smaller and smaller. So we still have the same horizontal asymptote, range, and domain. But that's going to change when we start doing shifts. So if a is negative, it's going to flip it over the x-axis. If we have something in the exponent, it's going to shift it right or left. K is still going to be up or down. So all the same transformations we've done in the past can still be done with an exponential function. So, how do we do it? Well, if I were you, I would just type it in the graphing calculator and sketch it. But then you still need to be able to state your domain and range. So we'll do the first couple together, and then you'll try the next two, and we'll be good to go. So the first thing says y is equal to 2 to the x power. So you just go 2 raised to the x power. And what I would do is press second graph and just look at the table. And plot as many good points as you can. You will need just a couple of decimals. So if we start at 0, 1, like we said before, so we have 0, 1. And then if we go to 2, we have 2, 4. Because remember, that's 2 squared. It's already going to be up to 4. And then by the time we get to 3, my bad, 1 was supposed to give us 2. I skipped it. And then 2 gives us 4. And then 2 cubed gives us 8. Going backwards, -1, remember that's a negative exponent, so it's like a reciprocal, and that's about as close as we're going to be able to get. So when you sketch this graph, just don't cross over the x-axis. And there you go. So your horizontal asymptote, it's never going to reach 0, so it's y is equal to 0. Your domain, you can substitute anything in for x. So x is equal to all real numbers. And your range, it's only positive numbers. So y has to be greater than 0. And there we go. That's your horizontal asymptote domain and range. And to move on to the next question, we can see that it's still 2 to the x, but now we have a transformation where we are going to flip it over the x-axis and vertically stretch it by a factor of 3. The a value still means the exact same thing as it has in other units. So now we're just going to go back to y equals, and we're just going to have negative 3 times 2 raised to the x power. So all we did was insert a negative 3. So of course you can graph it to see what it's going to look like. As I mentioned, it's flipped over the x-axis. But now, to graph it, just use the table again. Again, it's going to be falling so quickly that you're only going to be able to plot a few points. But then, of course, going backwards, just never get to the x-axis. So at 0, we're at negative 3. At 1, we're already down at negative 6. At 2, we're already off the chart. But then going backwards, at negative 1, we're at negative 1.5. At negative 2, we're at negative 0.75. And we're already ready to go. So now we're just going to not touch the x-axis and go down. So, horizontal asymptote is still y equals 0. Domain is still all real numbers. But if we look at the graph, all values of y are negative. So y is less than 0 is our range. Okay? And that's it. Just let your calculator do all the graphing for you, and you just have to analyze it. So why don't you press pause, try the next two, see how you do. Okay, so we have 4 times 1/2 to the x power minus 1. So 4 times 1/2, you can type 0.5 if you want to, raised to the x power, and minus 1. So that's going to change your horizontal asymptote, is what you should have noticed. So if you take a look at the graph, it's now decreasing. That's because it has a fraction. Remember, if the b value is less than 1, it's exponential decay. But this one crossed over the x-axis. And the reason why is because of the minus 1. It shifted the entire graph down 1. So if we look at the graph, negative 2 is going to give us 15, way above the graph. Negative 1 is going to give us a 7. 0 is going to give us 3. Now, if we think about that, remember, it's been multiplied by 4. So typically it crosses at 1, but you multiply it by 4, so now you're at 4, but you shifted down 1. That's how we get there. It's just using transformations. 1 brings us to 1, and 2 brings us to 0, and then it's just going to be a whole bunch of decimals, never hitting the horizontal asymptote of negative 1. So again, just carefully sketch your graph. Just never get to y equals negative 1. So y equals negative 1, that's your horizontal asymptote because it was shifted down 1. Your domain is still all real numbers. Your range, your graph is all above y equals negative 1. So y has to be greater than a negative 1. Okay, that's it. And finally, the last one, you saw a whole bunch of transformations done. So you have to carefully type that guy in. Again, you could just use 1/2, or you can just do 0.5 times 2 raised to the x minus 1. So that's going to shift the graph to the right 1. and plus 3, which is going to shift it up 3. Of course, take a look at the graph so you can see what it's doing. And then carefully go plot some points. So second table, your horizontal asymptote is now going to be at y equals 3. Because we shifted up 3. Okay, and now we're just going to go sketch some points. At 0, we're at 3.5, so we're right there. At 1, we're at 4. And at 2, we're at, I'm sorry, at 1 we were at 3.5. At 2, we're at 4. And then at 3, we're at 5. 4, we're at 7. And then at 5, we're going off the chart. So we're just going to graph. And there we are. Your domain, still all real numbers. But our range, it's above your horizontal asymptote. So y is greater than 3. Okay? Now, as you can see, look at your domain or your horizontal asymptote and your range. Notice how they're all the same. The only thing you have to do is look at is the graph above it or below it. So since the horizontal asymptote is 3 and the graph is above it, your range is y is greater than 3. In this example, our horizontal asymptote is 0 because we had no vertical shift, but it's below the graph, so y is less than 0. Okay? So that's it for exponential function graphs. This is Longo and I'm out. See you, bye.